How's everyone doing today? Doing well. Does anyone have any questions over the homework, first of all? We can go over those if necessary. Okay. Verse 67 and 69. Let's see. Yeah, 67. 1 plus or minus I over 5. Yeah, that's correct. Is that not what the book says? Oh yeah, yeah. I see what you're saying. Yeah, either way is fine. Whether you whether you write the book, yeah, the book might say, what does it say, 1/5 plus or minus 1/5 I, like that. Yeah, either answer is fine. The concept behind writing the answer such as this is that we have the real number separated from the imaginary number, and which is kind of how we normally write complex numbers. And I'm okay with either answer. Yeah. All right. Thank you, Natalie. I'll mark them down. 65. Okay, Madison. So for 65, we have x squared minus 6x plus 10 is equal to 0. So we'll plug that into the quadratic formula. And so we'll say x is negative b, so that changes a negative 6 into a positive 6. Plus or minus square root b squared is 36. Minus 4a C and over 2a. So under the radical we get 36 minus 40. So we know that's a negative 4. And so from there we can take the square root of negative 4. We know the square root of 4 is 2, but since it's negative, we will have an imaginary number, so 2i. Now, we've completed the square root, we've gotten rid of it, we've resolved that. Now our 2 on the bottom has to divide into both of these numbers on top. So this would make it 3 plus or minus 1 times I, or simply I. Okay. Were there other questions? Okay, Gabriel. Uh, 2 divided by 2 is just 1. Okay. So when we divide that, we can write down 1i, or we can just write down I, because the 1 is implied at that point. But again, when you're dividing by the 2, both numbers on top have to be divided by 2. right here. We took the square root of negative 4, which is 2i, and then we dealt with the 2 on the bottom. So this step is different than this step. So in this step, we're just working with that term becoming that term. Nothing else interacting with the denominator. Yeah, that's fine. Were there other questions? Sure. So 67, we have 25x squared minus 10x plus 2 equals 0. So negative b would make that a positive 10. We took the negative out and made it I. You mean the last problem, Amanda, or this one? Okay. So back here, sorry. Oh, yeah, yes. Whenever we have a negative number under the square root, it makes it imaginary, so we put the I there. Yeah. So square root of negative 4, we define I as square root of negative 1. I just wrote. So I is defined as square root of negative 1. So if we wanted square root of negative 4, we think of that as 4 times negative 1. And we take the square root separately. Square root of 4 is 2, and square root of negative 1 is I. Alright? Yes, Madison. We're working on this. So negative b is 10. B squared is 100 minus 4 times a, 25 times c, 2, and 2 times a would give us 50 on the bottom. Now, under the square root, that's 100 minus 4 times 25 is 100, times 2 is 200. So 100 minus 200 under the radical. So we end up with a negative 100 once we subtract those. And so the square root of negative 100 is 10i. Normally the square root of 100 is 10, But because it's negative, we know it's going to be imaginary, so we'll put the I there. And now that we have 10 plus or minus 10I over 50, we do want to reduce this, although 50 doesn't go evenly into 10 like we did with the last problem. What we can do instead is find a common factor that all three numbers have. So between 10, 10, and 50, all of them have a 10 in common, basically. So what we'll do there is we can factor out a 10 from the numerator, and then we can reduce the 10 and the 50. 10 divided by 50, that means 50 is 5 times 10, and so those 10s will cancel, so we still have 1 plus or minus I over 5. Okay. That's the thing we're most careful about, is when we reduce this expression, whatever numbers we reduce with the denominator have to come from both numerators. Because of the plus and the minus here, we can't reduce one part without also reducing the other part in the same manner. So that's an easy trap to fall into there. Right, and then 69 was 5x squared plus 1 equals 2x. Yes, that's correct, Lauren. Yeah, we can't go down any further than this. We talked about before how when you look at the answer in the back of the book, it may express it slightly differently than that, like 1/5 plus or minus 1/5 I, or 1 plus I over 5 and then 1 minus I over 5, but all three of those things mean the same. So any one of them is accurate. Now in this problem, number 69, first thing we'll want to do is, because it's not equal to 0, we'll take our 2x and subtract that over to the left. And make sure we fit it in between the terms so we have everything in proper order. Okay. 5x squared minus 2x plus 1. Now we can have, let's see, so b is negative 2. So negative b will make that a positive 2. Squaring a negative 2 gives us a positive 4. Minus 4 times a times c, and then that's over 2a, so 10 on the bottom. Under the square root, that is 4 minus, and this will be 20. So we'll have 2 plus or minus the square root. This will be negative 16. And then that's over 10. And this ends up being very similar to 67 as far as how we'll need to reduce this, because we have 2 plus or minus 4i over 10, completing the radical. But again, 10 doesn't evenly divide into either one of those numbers, so we can't just divide this. Instead, we need to find a common factor for all three values. So between 2, 4, and 10, all of them have a 2 in common. Let's factor out a 2 in the numerator. then finally reduce the 2 with the 10. And so that will give us 1 plus or minus 2i over 5, because 2 goes into 10 5 times. Alright. Are there any questions on that one? Is everyone okay with that? Okay. All right. Today we're going to look at section 1.4. Section 1.4 is on radical equations, equations quadratic in form, and factorable equations. Rather than write all that down, I'm just going to say other equations. But we want to start off looking at radical equations. So with radical equations, what we generally mean here is an equation that has a radical in it, which is simple enough. And the idea is that we might have, let me write that down, equations that contain at least one radical. Which means we have like a square root or a cube root and so on. Okay. And the way that we solve these equations is it's really the same approach we use for solving any other equation, which is if we want to get rid of something, we have to make sure we do the opposite to that. For instance, if we have, for example, square root of x is equal to 3, we think about how can we get rid of a square root. Well, we want to do the opposite of that. The opposite of taking the square root is raising something to the square power, or squaring that side of the equation. So the approach here is that we square both sides. So a square root of x squared equals 3 squared. Now when we square a square root, these are opposing operations, so they cancel each other out. It's just an x now. And then 3 squared is 9, and that gives us an answer. Okay. Now, if we have like a cube root of x equals -2, for instance, it's really the same approach. If we have a third root, we will raise both sides to the third power, or cube both sides, as we say. Again, whatever we do to one side of the equation has to be done to the other side. That's why we're applying this on each side. So that means we have third root of x to the third power equals negative 2 to the third power. So the third root cancels out the cube, or vice versa. And we end up with x equal negative 2 to the third power is negative 8. Okay. So those two examples are just kind of our, beginning or basic examples, just demonstrating the process. In practice, we know there's probably going to be a little bit more to this. In some cases, not a lot more, but it's a way to get started. So let me look at, and I'm just going to pick some even problems out of the book. This will be number 10 on page, looks like 117, yeah. And we have the square root of 3t plus 4 is equal to 2. Now, we go ahead and square both sides of the equation as we talked about. So that gives us and what I would encourage you to do is, and again, you can certainly skip some steps here, but if we already have the square root and we square both sides, we don't have to write down the step where we say, okay, the square root squared, those two things cancel, and we just write down our 3t plus 4. And actually the same on the right hand side. If we know we're squaring both sides, you don't have to write 2 squared. You can just go ahead and write down a 4 here if you prefer. It's really just a question of how comfortable you are with the material and how much you need to write down versus how much you already understand, and that just, I know, varies from one person to another. So it's whatever you need to do to feel comfortable, following your steps in your paper. Okay. Just don't make any massive leaps, because I need to be able to see the justification. Anyway, yeah. Now, we want to ultimately solve for the variable, of course, so in this problem we have t as our main variable. Now, we haven't solved many linear equations, which feels kind of weird at this point because we've talked about a ton of quadratic equations. But in a linear equation where we just have t to the first power, there's no t squared. We just want to get t by itself, so any constants that are here we want to subtract over, and then whatever's in front of the t will then divide. So we'll subtract the 4, so 3t is 0, and then divide by 3, and then 0 divided by anything is still 0, so we get t equals 0. Okay. Now, one thing that we want to do with not any radical equation, but specifically the square root equations, anytime we start off a problem with a square root in it and we use the approach that we end up squaring both sides, we have to be careful because sometimes we create answers that are not actually correct. What happens is that because we square both sides, we create the potential for a solution that is actually invalid, where the solution works for this equation, but it may not work for the original equation. And it really just depends on the problem itself when that occurs. So in these type of problems, we want to make sure that we take our answer that we got, in this case t equals 0, plug it back into the formula, the original problem in particular, and make sure that it still works. So taking a t equals 0, 3 times 0 is 0, plus 4 makes 4, square root of 4 gives us 2, and so that answer checks out. Okay? So it's important that we do check our answers here, because there will be occasions where we end up with an answer that is not technically correct. Let me show you an example where that applies. So we have the square root of x plus 2 equals negative 3. We'll go ahead and square both sides of the equation. So x plus 2, and then negative 3 squared will be a positive 9. And we subtract the 2, and we end up saying x equals 7. Fair enough. Pretty straightforward approach. We get x equals 7. Now we take our 7, we plug it back in. 7 plus 2 is 9, and then the square root of 9 is 3, but 3 is not equal to negative 3. So we actually end up with different numbers. Now again, the square root is here to begin with, so we assume that's a positive on the outside. Unless it specifically says it's a negative square root, we have to assume it's a positive here. So that's implied to be positive. And so essentially we get positive 3 equals negative 3, which is clearly a false answer. And I'm in the margin. Okay, there we go. It's not true that 3 and negative 3 are equal to each other. So by taking our result, plugging it in, and arriving at a false statement, this tells us this is not a solution. And in general, the problem has no solution. Okay. Now, it's possible that we have a question and we end up with 2 answers, and maybe one of them is a good solution and one of them is a bad solution. Or it could be that both are good or both are bad. It just depends on the problem itself, and us going back in and checking what happens when we plug our answer back into the original question. There's only a couple types of problems where we have to do this, but radical equations are one of those types of problems. So we have to make sure we check our answers. Not all radical equations, but square roots in particular. It turns out cube root problems don't have this issue. Only with square roots do we end up having this concern. All right. Let's do another problem from the book. Actually, let me make up another question. Okay, in this example, square root of x minus 3, and then after the square root we have another minus 5, and this is equal to negative 1. Now, the issue I want to bring up here is that we start off with the radical and another term on that side where it doesn't have a radical, so the negative 5 is outside of the square root. So we've been using this approach that when we get rid of the square root by squaring both sides. And we will still do that here, but before we can square both sides, what needs to be true, do you think? Or in this problem, what needs to happen before we can square both sides? That might be a better way of saying that. Yeah, we'll have to add the 5 on both sides first. And what happens is that we add the 5. That's because we want to get the square root by itself. So we get square root of x minus 3 equals 4. Now our square root is by itself on the left-hand side of the equal sign, and everything else is now on the right-hand side. Now we can go ahead and square. What happens is if we try to square this original problem, we end up with square root of x minus 3 minus 5 times square root of x minus 3 minus 5. We'll actually have to FOIL those together, and we won't completely get rid of the square root. We'll still have a square root present in the problem. And so it actually doesn't achieve what we would want it to do in that scenario, which is to get rid of the square root. It just makes the problem worse. So we add the 5 first. We now have a 4 on the right hand side. Now we can square. So x minus 3 is equal to 16. And then we can just add our 3 over after that. And we end up with x equals to 19. Now, once again, we still want to check our answer. Take our 19, plug it back in. 19 minus 3 gives us a 16. Square root of 16 is 4. And then 4 minus 5 is negative 1. So that is a valid answer. Okay. Alright, so far each of these problems we've looked at have resulted in linear equations for us to solve, so let's look at a couple of problems where they result in a quadratic equation that we need to solve. So this will be where's a good one? Oh, that's a good one. We'll look at number 20. Still on page 117. So I got the space. And number 20, we have square root of 12 minus x is equal to x. First thing we always check is the square root by itself, and in this case the answer is yes. So we can move to the next step and say we want to square both sides. Now on the left hand side, squaring that gets rid of the square root, as we know. But if we want to square our x, we know that's going to result in an x squared. And that's what makes this quadratic, is because we end up with an x squared term in the equation, whereas the other three examples we've looked at so far all just had an x, not an x squared, once we got rid of this radical. Now, whenever we have x squared in our problem, what should our general approach be to trying to solve this? Like in this example, what would we need to do next? We can move this x squared to the left. Good. And that would get it equal to 0. And that's the more general thing I was looking for, is that we want to make sure it's equal to 0 before we try to solve it any further. And that's how we generally work with quadratic formulas, or quadratic equations, sorry, is before we either factor or apply the quadratic formula, it has to be equal to 0. Now, you said move it to the left. I would actually say in this case, we would rather take the 12 and the minus x and move those to the right. And the reasoning is, x squared is already positive right here. we have a positive x squared. And in general, the problems are going to be much easier if we have a positive x squared than a negative, because it makes things less confusing when we either go to factor or plug into the quadratic formula. So in particular here, I would say let's take our 12 and our minus x and move those to the right instead. But the outcome is still the same, that we end up equal to 0. But I would caution you to make sure x squared is positive, because it just makes things a lot easier. Okay, so we have 0 equals x squared plus x minus 12. And so we look at this, we need, this is actually factorable. We need two numbers that multiply to negative 12 and add to positive 1. What would those two numbers be? 4 and 3, but specifically 4 and negative 3, right. Because we want to make sure we we want to make sure we include the signs, because I have to multiply to a negative but then add up to a positive. Yeah. Okay. I'm running out of space here. So we have x plus 4 and x minus 3. And so our two solutions are negative 4 and positive 3. Now, we want to, again, check those answers in the original problem and make sure both are valid. So x equals negative 4, we'll start there. 12 minus a negative 4, well, we're subtracting a negative, so we know that turns into a positive. 12 plus 4 gives us 16. Square root of 16 is positive 4, and x itself is negative 4, so we end up with 4 equals negative 4. Well, that's not true. 4 is not equal to negative 4, so we can rule out negative 4 as a valid solution. So now we'll try 3 instead, and hopefully that will work. If we plug in x equals 3 here and here, 12 minus 3 is 9, and the square root of 9 is 3. We get 3 equals 3. And so x equals 3 checks out, so that is our only solution in this case. Does anyone have questions on that? Let's do 26 next. We have 2 plus the square root of 10, oh sorry, this is 12 minus 2x equals x. Now, again, in this problem, similar to an earlier one that we saw, we have, besides just our square root, we have an extra number on this left-hand side. So, step 1, we'll want to go ahead and subtract that number over so that we can have the square root by itself on this one side. Now, this means on the right hand side we already had an x and then we subtracted a 2, so it's x minus 2. Now when we square both sides, again, the left hand side is 12 minus 2x, as we know, but on the right hand side, when we say square both sides of the equation, we mean we square the entirety of each side, which means we think of that side of the equation as being inside parentheses. Now, that means if we have a binomial like x minus 2, we end up having to square the binomial. We don't just square the individual terms, we square the entire expression. And that makes an important difference. So we have x minus 2 squared. We can think of that as x minus 2 times x minus 2, and we can go through and FOIL that, or if you're comfortable squaring a binomial, that approach works as well. So what do we get when we FOIL the right hand side? X squared minus 4x plus 4. Good. Yeah, because we do x times x is x squared, negative 2 times x outside, negative 2 times x inside, so that negative 2x plus negative 2x makes negative 4x, and then negative 2 times negative 2 is plus 4. Yeah, we're just foiling the binomials there. Now, we get down to this point, and again, we have an x squared in the problem, so it is quadratic. And we want that x squared to be positive, so let's move everything over to the right once again. So that'll give us x squared minus 2x minus 8. Okay. Now again, we want two numbers that multiply to negative 8 and add to negative 2. So what would those be? Two and negative 4, right? Yeah, they multiply to a negative and they add up to a negative, correct. Alright, and so we get our factorization, so our two solutions, or our two potential solutions I should say, is x equals negative 2 and x equals 4. But again, we want to make sure we check our answers. So x equals negative 2. 12 minus 2 times negative 2. So minus 2 times minus 2 is plus 4. 12 plus 4 is 16. Square root of 16 is 4. And 2 plus 4 gives us 6 on this side. Now we plug in a negative 2 here, so we end up with 6 equals negative 2. Definitely not a correct answer. So we know negative 2 is not valid in this scenario. So let's try the 4 next. 2 times 4 is 8. 12 minus 8 is 4. Square root of 4 is 2. 2 plus 2 gives us a 4 on this side, and we plugged in x equals 4 over here. So 4 equals 4. That is a correct answer, and that means that x equals 4 is a valid solution. That's about as difficult as these problems get. Well, at least as far as what we're gonna do. There are worse problems that you may remember from previous classes where we have two radicals and then a third term that's not a radical, and it's just crazy. And we're not going to do those. We don't have to worry about that. Anyway, so the next thing we cover in this section 1.4 we'll be talking about equations that are quadratic in form. Oh, sorry. Now, when we say equations that are quadratic in form, they're not quadratic, first of all, which means they don't start with x squared. Okay. It also means that the first exponent is twice as large as the second. And it means the third term is a constant. So let me show you some examples of quadratic or equations quadratic in form. You have to have all three of these requirements, or all three of these conditions, basically. So for example, we could have x to the fourth minus 10x squared plus 9 equals 0. We could have what else do we have? We could have x to the 2/3 power minus 5x to the 1/3 power minus 14 equal to 0. That would also be considered quadratic in form. And there's some others that we use. I think these are the two I would like to focus on. We don't do a whole lot with these, to be honest, but it's nice to understand what we're doing with them. Let's see. Could do a negative. I don't really want to, though. Yeah. Let's just do these two. That'll be good. Alright. Now, we notice that these fit both or all three conditions. They don't start with x squared. The first exponent is twice as large as the second. So 4 is the same as 2 times 2. And 2/3 is the same as 2 times 1/3. Okay? And the third term is a constant in both cases, the 9 and the negative 14. So these are sometimes we'll refer to them as quadratic-like equations because they look and behave like quadratic without actually being quadratic. So the idea is that we can still factor these exactly the same way we would factor a quadratic equation. Now, one thing that happens with quadratic equations, such as this one that we just solved, we don't really talk about is when we do the factorization here, x squared minus 2x minus 8, we get x plus 2x minus 4. And we understand where the numbers come from based on these two requirements. We found two numbers, that's where those numbers came from. But why do we use x and x? Well, because x times x gives us x squared. Now, let's work this first one, x to the fourth minus 10x squared plus 9. I may not have enough room here, but we'll go with it. So, first thing we need to do is make sure we choose our correct numbers with the 9 and the negative 10. And those numbers would be negative 1 and negative 9, right? Yeah, they'll both have to be negative to be able to multiply to a positive and add up to a negative. Yeah, but specifically this pair. So we know we can create our factorization. One of the factors will have minus 1 and the other will have minus 9. The question is, what is going to go in the first part here? How do we split up the x to the fourth? So when we think about how to split up that x to the fourth, the first term, there's two ways we can think of that. One is that we can just divide the exponent by 2. Divide 4 by 2, so it's going to be x squared and x squared. The other thing is, whatever is here is actually going to be identical to the middle term. So if we have an x squared in the middle, we know we're going to get an x squared and an x squared. The same thing is actually true of our quadratic equation. We factor x squared to x and x, and then again, this middle term is x. That tells us what both of those are going to be. Okay. So it's really two different approaches. Either cut this one in half, which is easy enough, or just take whatever's here and write it down here. So x squared and x squared. Okay. So we have x squared minus 1, and we have x squared minus 9. Now, we could factor these, or we can just solve them as they are. We can say x squared equals 1, and x squared equals 9. And in this case, we would just take the square root on both sides. So x is plus or minus the square root of 1, which is plus or minus 1. And then x is plus or minus the square root of 9, which is plus or minus 3. Okay. So I barely had enough space there for that problem. Any questions there? I think most people are generally okay with the x to the fourth problem. Turns out the x to the 2/3 problem is the one that drives most people crazy, so I guess we'll do that one next. Let's see, it said minus 5 and minus 14. Actually, because we didn't take any square roots, we actually squared both sides rather than taking a square root. We don't have to check the answers. I know it feels like we should after all the stuff we talked about in the first part of this section, but unless we start off with the square root in the problem, we don't have to check our answers, at least in these types of equations. There are other problems that we'll have to check our answers in, but that usually is if we have a rational equation where there's a expression on the bottom of a fraction, or else we have a logarithmic equation. Yeah, those are the only three types that to worry about. Now again, we start off with the same idea. We want two numbers that multiply to negative 14 and add to negative 5 to establish our factorization. So those would be negative 7 and 2. Good. So we're going to set up our factorization, and we know one of them is going to have minus 7 and the other is going to have minus 2. But what is going to be in the first part of each of these parentheses in this case? Anyone have an idea? 1/3? Oh, yes, thank you, August. That was my bad. Yes, it'll be x to the 1/3 in both of these. because again, 1/3 is half of 2/3, or we could just, since we have x to the 1/3 in the middle, we know we're going to just put that in both places. Now, this actually creates a more difficult equation to solve, as you can imagine. We still set it up the same way. We say x to the 1/3 equals 7, or x to the 1/3 equals -2. Okay. What does it mean, or how do we get rid of a 1/3 power, though? What will we have to do to both sides of the equation to cancel out the 1/3 exponent? Does anyone happen to know that? And that's okay if you don't know that one. That's a little bit trickier. Cube them, right. We haven't talked about this too much, but x to the 1/3 power is actually the cube root of x. Okay, just like x to the 1/2 power is the square root of x, or x to the 1/4 power is the fourth root of x. Anytime we have a fraction like that in our exponent, that actually refers to a root that's taking place. And whatever's on the denominator tells us the root. If we had x to the, let's say we had x to the 4/3, that would be the cube root of x to the 4th. The 4 would still be an exponent, but the 3 is the root on the denominator. And that's just a property of exponents. So, if we cube both sides, that gives us x equals 7 cubed, and x equals -2 cubed, and 7 cubed is 343, and -2 cubed is -8. Alright. Are there any questions on these? Especially this last one. Okay. Let's go ahead and look at homework for this section. This will be on page 117. I'm going to go ahead and give you 49, even though we didn't cover it, but see what you can do with that. It's not imperative you work through that successfully, but I just want to see if y'all can find different ways to solve that one. Let's see, 49, then let's do 61. $79 and 83. Now, we didn't talk about these last two yet. If you want to work them, you can. I wanted to go ahead and get them down as part of the assignment for this section, but those will be the first things we talk about on. Oh, also, there's no class on Monday because that's Labor Day. So our next class will be on Wednesday of next week. So keep that in mind. There won't be any lecture on Monday because of the holiday. So go ahead and look at these for now. And that's fine, William. Natalie told me you were having some problems. That's fine. Anyway, so remember, no class next Monday. So next Wednesday will be our next class, and we will continue from there. I hope you all have a good weekend. Hopefully you don't have a lot to do on the weekend. You can enjoy the extra day off. But take care, and I will talk to you next time. Bye. Final exam will be cumulative. Yes, we can talk about that a little bit more later. Each of the individual exams will just be over the material that they cover, although by the very nature of the subject, math tends to be somewhat cumulative anyway, because we continue to build on what we learned throughout the semester. So technically they're not cumulative, but also technically they are in a way. So. Y'all take care.